Hello. So now I'll record some linear algebra lectures here. Okay, let's start. So this is the first lecture. This is the first recording for the linear algebra. So this is the first recording. So the idea is to introduce the course. So we have the setup, and so the course is linear algebra. So this is actually should be a second course, or for those people who have a background on proofs. So the focus here is concepts rather than computation. So our topic has the list of topics are the following. We will start with vector space or vector spaces, and then we will go to linear maps between vector spaces. And then the third one will be eigenvalue, eigenvector, and then invariant spaces. And then the fourth, let's number this 1, 2, 3, 4. Fourth will be inner product spaces. And then the number 5 will be operations on inner products. Spaces. 6 and 7, we will go to, let me make this smaller. We'll go to operators in real complex vector space, and then we have real vector space, real real product space. Wait, let me check. Real vector spaces. And then the number 8, we will go to determinants and trace. So the text that we will be following with is a linear algebra done right by Sheldon Axler. You get the latest edition, or you can use the old edition. All right. So this is not very formal, of course, because this is just a review on my part, but I'm trying to record so that it's proper. So let's start with the first topic. So what is linear algebra? So you can read many books and then compare the definitions. But here I will just say that this is linear algebra in the context that we will have is the study of linear maps. It's the study of linear maps. So these linear maps we will formally define later, and in this course we will study linear maps in finite dimensional. dimensional. So this dimensional, we will also formally define them vector spaces. So vector space, we will also formally define them later. Note that vector space, and then of course a vector space is just a structure with addition and scalar multiplication. And here we will focus to the field or the ring, the base field here. Here is just the set of real numbers or the set of complex numbers. Okay, so we will utilize your previous knowledge from earlier courses such as calculus in high school math. All right, let's continue. So let us begin by recalling the definition of a complex number. So a complex number uh, is just an ordered pair, um, A, B, and then A and B here of real numbers. Here A and B. And then, of course, we write AB, A plus BI. And then here our I squared is -1. This is from high school. And then let us set or C be the collection of all complex numbers. A and B here are reals. So this is the set of all complex numbers. And of course, we have addition and defined on complex numbers as follows. So addition is if we have A plus BI and then C plus BI complex numbers, this is the addition or the sum is just A plus C as our first real number part, and then the complex part will be B plus D. And then the multiplication is defined as follows: B I and then C plus BI. It's just easy. You just have to recall that I squared is -1, but for the sake of easy, let me write the answer here: AC minus BD plus J, AD plus BC times I. So here, our A, B, C, and D are all real numbers. If we have an element, okay, so that's the definition. So some remarks: if A is a real number, you can identify it with, say, A plus 0i, so that our set of real numbers sits inside the set of complex numbers where the imaginary parts are just 0. So for this part here, you don't need to memorize. You just recall that I squared is -1, and then this is an example. So if we have 2 plus 3i, and then we have 4 plus 5i, you just do the usual thing. So this is 2 times 4 plus 2 times 5i plus 3i times 4 plus 3i times 5i. And then, of course, I squared is -1. So this is just 8 plus 10i plus 12i plus -15, because I squared is -1 and 3 times 5 is 15. And then we get -7 plus 22i. So you don't need to memorize this part here. It's just an easy consequence of some algebraic manipulations here. All right. So before going further to define a vector's to state some definitions, let us first recall some properties of complex numbers. So properties of complex, not complex numbers, but operations on complex numbers. So let's call them complex arithmetic. So the first property is commutativity. Commutativity of operation of addition and the operation of multiplication. So here W plus Z is equal to Z plus W, and then also WZ is equal to Z times W for all W and Z in the set of complex numbers. Number two, we have the associativity. Associativity. Okay, my spelling seems messy. Associativity. So the first is commutativity. The second is associativity. So this is first we got with addition. So if we have this order, this is also the same by if we group Z1, Z2 here, and then Z3. And then, of course, this is associativity with respect to addition. Okay. And also, if we have multiplication, so the same. So we have Z2, then Z3. This is also equal to Z1, and then Z2 here, and then Z3 here. So for all Z1 and Z2 and Z3 in the set of complex numbers. So for the identities, okay, we have first the additive identity. So we have lambda plus 0 is equal to lambda, and then 1 times lambda times 1 is equal to lambda for all lambda in the set of complex numbers. And here we have the additive identity, and then here we have the multiplicative identity. Of course, 0 plus lambda is also equal to lambda because of the commutativity property that we have earlier. And then the fourth one is the multiplicative inverse. So for the multiplicative inverse, so for all alpha in the set of complex numbers, we get, and alpha is not 0. So there exists a unique. So this one is there exists a unique. There exists a unique beta. It's also a complex number such that your alpha times beta is equal to the identity 1. And then the fifth property is the following. So we have distributive. distributive property. For distributivity, is we have lambda and then we have alpha plus beta is equal to lambda alpha plus lambda beta. This is for all lambda, alpha, and then beta in the set of complex numbers. So, yeah, that's it for this property. If you have algebra background, says that your set of complex numbers, if you have algebra background, C is a field. Okay. So another remark in this series, or we will denote F to be our field, and then F is just C or R. We will use other fields. I think the sophistication of C and R is enough. And then, of course, this is because we're just following the book. So, okay. So F here, our base field, and then elements of F are called scalars. Okay. And then for Z, suppose our Z is a general element of F, and then we have M greater than 0, M integer, then define the n tuples, Z to the M, it's just Z, and then multiply Z to the M is just product of M times M copies of Z. All right, we will recall from calculus that we have and C to the N and R to the N. Recall from our calculus that we have R2 here, we have familial notion of R2 and R3. So from Math 36, or maybe other numberings. So we have A, B, C. The idea is we generalize to N copies of R. Okay. But before going further, let me have some remark here. So if we have Z to the M raised to N, this is just Z to the M times N. And of course, if we have WZ raised to M, this is just W raised to N and Z raised to N for all W and Z in our field F, where F here will maybe either C or either or R. Now we add some definition. The next definition is a list of length N. So a list of length N is an ordered collection of n objects. So we say objects can be numbers or anything because we're in abstraction. So we an element, a list, we can write it as x, just x1 to xn, and then we have to remark because we can some people um, call this as an n-tuple of objects, but yeah, it can be depends on your reference. So if we have two lists are the same, or two ordered pairs, or two triples are the same if they are equal component-wise. This is from your ordered pairs definition in Math 101 and in your calculus. They are equal if component-wise they are equal. Now we will introduce another definition. We have this f to the n. So this is just is the set of all lists of length n. So n here is for the length n. So this is defined as follows. We have x1 up to xn, where xj is in f, and j here is runs from 1 up to n. So this is our list. And then for x1 up to xn, we call x of j the j coordinate, or the sometimes it's called j component, the j coordinate of our list x1 to xn. Sometimes component, as you can recall from your calculus. And we have some proposition here. But before the proposition, how do we add list? So we define addition in our f to the n. So the first, if we have x1 here, and then x to the n, the first element, the first list, and then the second list is y. Then let us call this, this is our x, this is our y, y to the n. The sum, okay, the sum is just x1 plus y1, and then up to xn plus yn. So basically, what you do is to add the component-wise. You add them component-wise. Okay. And from that proposition, that definition, we have the following theorem or proposition. It's not very big, but I can call it theorem also. If we have x and y in the Fn, then x plus y is equal to y plus x. For the proof, we have let x equal to this list and y equal to this list. The elements of f to the n, then x plus y is just x plus y1 xn plus yn. Okay, let me repeat. Okay, this is first define it as x1 and then xn plus y1 yn. So this is just x1 plus y1. Oh wait, it's supposed to be comma and then end with xn plus yn. And then because this is by definition, and then because of the commutativity of f, because f is just c or r, which is commutative, has commutative properties, then x1, you can rearrange y1 x1 and then yn plus xn. And then what? We can now have it as y1 yn plus x1 xn by definition of addition fn, and then this is just y plus x. So the reasons are provided earlier. So let me write this here. Just by definition, this by commutativity of our f, and then if you end the proof, you can either put a box, but make the box this. Sometimes you can use q, e, if you are a classic person. Box with is also okay. Okay. So that's it for our first proposition. Then we go to another definition. Denote 0, the list of length n of all zeros. So 0 here. Sometimes we put some r at the top to distinguish this from 0. But sometimes we just get it from the context by abuse of notation. And then recall our picture of vector addition. So if we have vector A here, and then we have vector B, okay. So how do you add vectors? So we have a vector A and then vector B, and then here we have A plus B. And then if we have vector A here, and then vector B goes this way, then this one will be the resultant A plus B. So I will not be doing details for this because I believe this is your visual picture in multivariable calculus. All right. Now, also, if we have x be in our f to the n, the inverse, the additive inverse denoted negative x is, yes, if x is equal to this, negative x is just negative x1, negative xn. All right. So the our x plus negative x is just our zero vector. And then, of course, if this is your vector, your least x, this is your negative x. Here I write A, but you can use other letters. Now, we have already defined vector addition. And then the other operation is, I'll state this as a definition, the scalar multiplication. We will go back to this later. This is also familiar from our calculus. The product of a lambda in our f and a vector in f to the n computed as follows. So this is the scalar multiplication is defined this way. So if we have lambda and then x1 to xn, so this is just lambda x1 and then lambda xn. And then, of course, from your calculus, if we have x here, then if your lambda is 2, so 2x increases your lambda, and then 0.5x decreases your lambda, decreases your x, or the length. So, yeah, that's it. This is just a recall from, remember, this is a conceptual class, of less computations will be done here. And I will have a digression, meaning this is not part of the course, but if you have some algebra, or you have already taken algebra, you may look at definition and examples of fields. So examples include Z, no, not Z, our R, our C, and our finite field Z, let's say P prime, or you can also have Z sub Q or F sub Q. So you might check, you might take a look at this. That's it for a little digression. And now we are ready to define a vector space. So a vector space is a set V along with addition and scalar multiplication on V, such that the following properties hold. Number one, so this is commutativity of addition. So if we have u plus v. This is equal to v plus u for all u and v in our vector space V. So this is just for the addition. And then we have associative. If we have u plus v plus w, we can have u plus v plus w, which is for all v, u, and w in our vector space V. And if we have we add scalar multiplication, we have a and b away. So next associativity is a b times v. This is also a b v for all a and b in our field F, and v in our vector space W. And the third property that it should satisfy is the existence of additive identity. So there is an element 0 in V such that your 0 plus V small is equal to V small for all our V small in the V. And number 4 is additive inverse. Remember that when you're defining additive inverse, you should have the additive identity defined first. So for all V in the vector space V, there exists an element W in V such that your V plus W here is equal to the 0 or equal to the additive identity. Okay? And for the fifth property, we have the distributive multiplicative property, the existence of multiplicative identity. So for the multiplicative identity, we have there exists a multiplicative identity in no, it's this one here is the one in our scalar. So this is equal to V for all V in our vector space. And number 6 is the distributive property. So we have alpha, and then u plus v is equal to alpha u plus alpha v. And then, of course, we have a plus b here times v. This is also a times v plus b times v. Here, for all alpha in F, and for all u and v in the vector space V. And here we have for all A and B in our F, and for all V in the vector space V. So again, a fancy way to say this is that V is an abelian group, and then that satisfies some extra properties related to scalar multiplication. So this is a fancy way of saying this if you have some algebra, abstract algebra background. Of course, you have a little bit, but I'm not assuming them. So we can now also define elements of a vector space. So we call an element of a vector. These are called elements Vector space are called vectors, or sometimes we call them points. Here we don't distinguish points um, from vectors. So extra remark. The scalar multiplication in V depend on F. Thus, thus we need to be precise and say vector space over our field F instead of vector space only. Okay. So for example, we have R to the N is a vector space over R, or we call this real vector space. Then C to the N is a vector space over C, or we call this a complex vector space. So let's have some common vector space. So of course this is the simplest and useless vector space. Okay, our R is also over itself. Then R2, R3, and Rn are vector spaces over R. And then we have some special vector space here. We have if F infinity. So this is just a collection of sequences xn. Okay, let me write it this way: x1, x2, and then it doesn't stop. Here xj is in F, and our j here is running from 1, 2, and then doesn't stop. So this is the set of sequences of elements of our field F. So of course, we can verify the above samples satisfy the vector space properties. Okay. Another example is, say, example number 5. So we have F here and then S. Here S is a set, and then F to the S is the set of functions from our S to F. And then how do we define addition? So what are elements of F to the S? So they are functions. So F, G in F to the S, F plus G of X here is defined f of x plus g of x, and then for lambda in f, lambda f of x is equal to lambda times f of x. This is for all x in ours. F in our set, because they are just functions from set f to f. So examples of these are follows. If our f is equal to the real numbers and s be just the interval 0, 1, then f to the s is just functions f from 0, 1 to r. This is the set of functions from 0, 1 to r. So these are set of real valued functions from our interval 0, 1 to, of course, real values. So we can remove to r. And then this definition here of f to the n, you can think of it as f to the 1 to n. So these are just functions from set of functions from 1 to n to our f. So for example, this is a special case. And also f infinity as f1, 2 doesn't stop. So this is a more abstract example, but you can ponder on it. So yeah. Now we are ready to define or to state some properties of a vector space. So the first, let us have some remarks first. We will meet more examples later of vector space. But first, we will develop some theory first. So theorem of vector space has a unique additive identity. The proof here is standard. Suppose we have 0 and 0 bar are both additive identity. We need to show that they are the same. Then 0 is just 0 plus bar. This is just 0 plus 0, since is additive identity. This is commutativity. It is equal to 0, since 0 is an additive identity. This is the reason thus 0 and V has a unique additive identity. All right. Okay. Any question on this proof? I think it's clear. We have some other similar theorems. Every element of vector space has a unique additive inverse. Then another one, if we have, before going further, let me fix some notation first. If we have now notation, if V is in a vector space, negative V is the additive inverse. And then V plus negative W, or wait, let me write it differently. V is equal to W minus V. So we write this one as this one, this as this for easy annotation. So now, from now on, we fix V is V denotes a vector space over our field F. If I fail to mention, so this is our convention. All right. So before we end today's video recording, let me end with some properties. Okay, so we have here, the first one is 0 times V is equal to the 0. This one is the 0 in our vector space for all V in our vector space V. And then the other one is we have negative 1 times V is equal to negative V for all V in our vector space. I will prove this one. So for V in the vector space V, we have V plus negative 1 times V is just 1 plus negative 1 times V. This is from property. And then this is, of course, 0 times V. And then from above, this is 0. This says that negative 1 times V is the additive inverse of V. Thus, negative V is equal to negative 1. Because our additive inverse must be unique. So if this property holds, then negative 1 times V must be the additive inverse of V. Okay? So for the next series, we will cover subspaces and then direct sums. And then we go to linear independence. Of course, associated with that is a span, basis, dimension. So I think we will end the first recording here.